Hello everyone and welcome back. This is part 2 of lecture number 15 for General Chemistry 2. This is the second acids and bases lecture. In the first half we learned a lot about the pH scale, how it's defined, how we can calculate these values. We learned a few key equations. Here we're going to continue on and learn how we can calculate pH and pOH for weak acids and bases, and then later towards the end of the lecture we'll learn about salts. So acid and base strength, as we learned, is measured on the pH scale. A low pH means you have a strong acid and thus a weaker conjugate base. A high pH means you have a weak acid or a very strong base. Less commonly, we can consider pOH equals negative log of OH minus. So a lower pOH equals a higher pH and vice versa. It's very easy to calculate for strong acids and bases, as we saw in the previous lecture. Strong acids dissociate completely, so H3O plus concentration just equals the acid concentration. Strong bases use this same logic. Just watch out, if it's a strong base with two hydroxides, make sure you double that concentration. But it gets a little more complicated with weak acids and weak bases. We're going to see here how we can handle those types of compounds. Let's start by considering the strong acid HCl. HCl is a strong acid whose dissociation is shown below. Now, as we learned in lecture 1, or the first acids and bases lecture, I should say, HCl and Cl- are a conjugate acid-base pair, but Cl- is not a strong enough base to take the H3O plus back from H3 take the H plus back from H3O plus. So this reaction cannot run in reverse. This is why we use a single arrow, not an equilibrium arrow. Anytime we show the dissociations of strong acids or strong bases, we use a single forward arrow because these reactions move in the forward direction only. They are irreversible. The reverse reaction does not occur to any significant extent. Now let's think about the weak acid HCl. This is hydrocyanic acid. This is a weak acid whose dissociation is shown here, HCN plus H2O. We show those double arrows because it's an equilibrium reaction, forming H3O plus and CN minus. HCN and CN minus are a conjugate acid-base pair. CN minus is a strong enough base to take the H plus back from H3O plus. So since the reverse reaction does occur to a significant extent, we use an equilibrium arrow when writing the reaction. Because it's an equilibrium reaction, this means there is an equilibrium constant K. So for acids, bases, and equilibrium, if we're looking at weak acids, so A here just represents whatever the anion is. It's just a generic acid. In the previous example, A would be representing the CN, or it just represents whatever the anion is in the weak acid. So HA plus H2O forms H3O plus and A minus, the leftover anion. Here we define Ka as the concentration of H3O plus times the concentration of A minus divided by the concentration of HA, again noting that H2O is not included because it's a liquid. So the stronger the acid is, the more H3O plus is going to be formed, meaning you're going to have a larger Ka value. So the bigger Ka is, the stronger the acid is. We can also define this for weak bases, where we can say that A minus plus H2O forms OH minus and HA. So Kb, so here Ka, the equilibrium constant of a weak acid. Here it's Kb, equilibrium constant of a weak base. This is OH minus over H, or times HA divided by A minus. So a stronger base means we have a larger Kb value. And I do want to note here that a stronger acid does not mean we have a higher concentration of HA at equilibrium. It means the HA is more reactive and thus more H3O plus is formed. For the strongest acids, there's actually going to be very little HA remaining because more of it gets converted in this direction. And we could make the same statement for bases. So how can we relate Ka and Kb through Kw? Let's look at those two previous generic reactions we set up. HA plus H2O forms H3O plus and A minus, and then A minus plus H2O forms OH minus and HA. If you add these two reactions together, you'll find that the HA and the A minus cancels, which gives 2H2O, forms H3O plus OH minus, and we should notice here that this is the Kw expression we defined earlier or in the first half of this lecture. And so what this means is Ka times Kb equals Kw, which is 1 times 10 to the negative 14th. And this is for an acid HA and its conjugate base A minus. So using Ks to compare acid and base strength, when we compare two different substances, the bigger its Ka is, the smaller its Kb is going to be, meaning it has a stronger acid and a weaker conjugate base. On the flip side, the lower the Ka value is, the bigger the Kb is going to be, meaning we have a weak acid or a strong conjugate base. So question, which is a stronger acid? And second question, which is a stronger base? So pause the video and see if you can answer these two questions. All right, the answer is here. And the first one, you should note that HA is a stronger acid than HX because the Ka value for HA is larger. Then second question, which acid has the stronger conjugate base? The answer here would be HX. HX would have the stronger conjugate base. Remember that if you have the smaller Ka value, you're going to have the bigger Kb value, and thus you will have the stronger conjugate base. All right, so let's review some equilibrium calculations. Acetic acid has a Ka of 1.8 times 10 to the negative fifth. What is the pH of a 1 molar acetic acid solution? I do want to note that this is not the actual formula of acetic acid. Acetic acid has the chemical formula HC2H3O2. I'm just using this designation here to apply this. You can use kind of the logic we're using this problem to apply it to many of the problems we are going to see. So we've got 1 molar HA. What we do need to do here is set up an ice table. So on these acid-base equilibrium calculations, if you're dealing with a weak acid or a weak base, because they partially dissociate, you will need to set up ice tables. So we have 1 molar HA and we have 0 molar of the H plus and the A minus. Our changes are going to be minus X and plus X for both of these, giving us equilibrium concentrations of 1 minus X and then X and X for the H plus and A minus. Then we can set up our Ka expression. Ka equals H plus times A minus divided by HA. We can plug these values in. X is plugged in for H plus and A minus, 1 minus X plugged in for HA. All of this is equal to that Ka expression, or that Ka value. So this expression is equal to 1.8 times 10 to the negative fifth. What I want to note here is that we can use the small x approximation because this value is times 10 to the negative fifth. We can essentially cross out the minus x, and so this functionally just leaves us with x squared equals 1.8 times 10 to the negative fifth. Therefore, x equals the square root of 1.8 times 10 to the negative fifth. So x is equal to 4.243 times 10 to the negative third. So on these problems, very similar to the ice problems you saw in the end of Unit 2, once you solve for x, x will give you the concentration of H plus, or H3O plus to be more specific. So here, H plus equals that x value, 4.243 times 10 to the negative third molar. And finally, we can calculate the pH by taking the negative log of the H plus concentration. And our final answer is 2.37. All right. I've got one problem for you to try. So what is the pH of a 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the negative fifth? So follow along with the steps I walked through on the previous problem and see if you can come up with the answer here. All right, correct answer on this one is 2.59. You should have found that the pH equals 2.59. One more problem for you to try. Find the pH of a 0.5 molar HF solution given the Ka of HF as 7.1 times 10 to the negative fourth. And the correct answer here is 1.72. All right, now let's look at a weak base problem. If the Kb value of NH3 is 1.8 times 10 to the negative fifth, what is the pH of a 0.75 molar solution of ammonia? So our strategy here is we're going to start by writing out the dissociation reaction that the Kb value describes. Then we can set up our ice table and equilibrium constant expression. Finally, or third, I should say, we can plug in and solve. In this case, since we have a base, we're producing OH minus, so we'll find the OH minus concentration, and then finally, we can use that OH minus concentration to find the POH, and then use that to find the pH. So let's go through these steps. We're going to start by writing out the dissociation reaction. So this is NH3 plus H2O forms NH4 plus and OH minus. Second, we're going to set up our ice table. Our initial concentration is 0.75 molar. Water can be ignored. Initial concentrations of the products are both 0. Here, everything has a coefficient of 1, so our change would be minus X for NH3 and plus X for these two products, giving equilibrium concentrations of 0.75 minus X for NH3 and just X for both products. Set up your Kb expression, so Kb equals products over reactants, so the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3, and again noting here H2O is not included because it's a liquid. Plug in these values, so X for both products, 0.75 minus X for the reactant, and this is all equal to that value given, 1.8 times 10 to the negative fifth. We can use the small x approximation again here. So we get x squared is equal to 1.8 times 10 to the negative fifth multiplied by 0.75. X is therefore equal to the square root of 1.35 times 10 to the negative fifth. And so x is equal to 0.003674. With that x value, this tells us the OH minus concentration. So with this, we can find the POH. So the POH is the negative log of the OH minus concentration. So this is around 2.435. And then finally, using that expression we set up earlier, pH plus POH equals 14, we can solve for the pH. We should find that the pH is equal to 11.57. Okay, I would like you to try this problem, so very similar steps to the problem I just walked through. Hydrazine, N2H4, is an inorganic compound used in various rocket fuels and for the gas precursors in airbags. It has a Kb of 1.3 times 10 to the negative 6. What is the pH of a 0.15 molar solution of hydrazine? Please pause the video and give this problem a try. All right, the answer is the pH is 10.65. 10.65 here. Again, if you had trouble finding this answer, just go back through the example problem I just showed. This problem here follows essentially the same steps, just working with N2H4 instead of NH3. All right, now let's talk about salts. So a salt is just a name we use to describe ionic compounds. As we learned in the previous acid-base lecture, these are typically formed as a product in an acid-base neutralization reaction. I do also want you to recall that when you learned, or what you learned about in Gen Chem 1, that most ionic compounds will fully dissociate in water, now depending on solubility rules. So depending upon what ions are contained in the salt, an aqueous salt solution might be neutral, it could be weakly acidic, or it could be weakly basic. Neutral salt solutions are typically formed from the reaction of a strong acid with a strong base. So hydrochloric acid plus sodium hydroxide, this forms sodium chloride and water. The salt NaCl formed in this reaction will dissociate into ions which are both neutral. That NaCl dissociates into Na plus and Cl minus. Neither the Na plus ion nor the Cl minus ion will react with the surrounding water. And to show that in a little more detail, again, if you put Na plus with water or Cl minus with water, they will not react with them. They will interact, so recall the ion dipole forces we learned about back in Unit 1. So these ions will interact with water, but they do not actually react with water. They will not cause the formation of H3O plus ions or OH minus ions. And so because of this, an aqueous solution of NaCl will have a pH of exactly 7. It is neutral. It does not form Na, any H3O plus, or OH minus. All right, then my question at the bottom here, what are some other examples of ionic compounds that will form neutral aqueous solutions? These neutral salt solutions, what is common is that their anion should be essentially I'm using quotes here, the conjugate base of a strong acid. So hydrochloric acid, hydrobromic acid, hydroiodic, the other strong acids we learned about. If you have the anion from a strong acid in your salt, it's likely to be a neutral salt. Similarly, if you have the cation from a strong base, so Na from sodium hydroxide, or K, or Rb, Cs, etc. Any of those cations that came from a strong base, when you put those in tandem with the anion from a strong acid, you're going to have a neutral salt solution. Next, let's look at basic salt solutions. The reaction of a weak acid with a strong base will produce a salt which is weakly basic. So here we have HF, a weak acid, and KOH, a strong base. So you can kind of think of it like you've got a weak acid, a strong base. The base is stronger, so the resulting salt is weakly basic because the base is stronger than the acid. Here, when we complete this neutralization reaction, we see our two products are KF, potassium fluoride, and water. Now K plus is neutral, like all group 1 and metal 2 ions, but F minus, formed from that dissociation of KF, F minus is the conjugate base of a weak acid, which means it is a weak base. Since it is a weak base, that F minus ion can take a proton from water to form a small amount of OH minus. So to show this in more detail, again, K plus, a group 1 metal cation, it's the cation from a strong base. It does not react with water. But F minus is the conjugate base of a weak acid. Specifically, it's the conjugate base of hydrofluoric acid. Because it is weakly basic, it will react with water to reform some hydrofluoric acid, as well as, importantly, a small amount of OH minus. And this small amount of OH minus results in that aqueous solution of KF being weakly basic. And so it should have a pH greater than 7. What are some other examples of ionic compounds that will form basic aqueous solutions? Again, anytime you have a group 1 or 2 metal cation, so the cation coming from a strong base, mixed with the anion from a weak acid, that's going to result in a basic salt solution. And finally, acidic salt solutions. These result from the reaction of a strong acid with a weak base. They produce a salt which is weakly acidic. So for example, HBr plus NH3, HBr, hydrobromic acid, a strong acid, reacting with the weak base NH3. NH3 accepts that H plus and forms NH4 plus, and we get Br minus. Br minus is neutral. It does not react with water because it is the conjugate of a strong acid, HBr, hydrobromic acid. But NH4 plus is the conjugate acid of a weak base. It's the conjugate acid of ammonia, NH3, meaning it is a weak acid. So when this salt dissociates into its ions, we have a weak acid that is formed, and that NH4 plus ion can react with water. It can donate a proton to water to form a small amount of H3O plus. So to show this in a little more detail, again, the Br minus ion does not react with water because it is the conjugate base of a strong acid, or it's the anion left behind from the strong acid. But that NH4 plus ion is weakly acidic. It will react with water and donate a proton to it. We reform some of that NH3, the ammonia, and importantly, we form a small amount of hydronium ion H3O plus. This results in that aqueous solution of NH4Br as being weakly acidic, and so we would expect that its pH would be less than 7. What are some examples of ionic compounds that will form acidic aqueous solutions? Anytime you have a mixture between the conjugate acid from a weak base and the anion from a strong acid. So again, if you have the conjugate acid of a weak base plus the anion from a strong acid, this results in an acidic salt solution. So to summarize everything we covered here, some general guidelines. Does the salt contain a group 1 or group 2 metal cation? The cation is therefore neutral. Yes. Oh, sorry. let me back up here again. Does the salt contain a group 1 or group 2 metal cation? Oop. If yes, the cation is neutral. If no, the cation is a weak acid. So this is a series of steps you can walk through. Start by looking at if that salt contains a group 1 or group 2 metal cation. If it does, the cation is neutral. If it does not, you can assume the cation is a weak acid. Similarly, you can analyze that salt and look at, does that salt contain the conjugate base of a strong acid? If yes, the anion is neutral. So here's the 7 conjugate bases of these 7 strong acids. If no, you can assume the anion is a weak base. If you have a neutral cation and neutral anion, you've got a neutral salt. If you have a weak acid cation and a neutral anion, you have an acidic salt. If you have a neutral cation and a weak base anion, you have a basic salt. Now, what if you have a weak acid cation plus a weak base anion? Then what? This involves slightly more investigation. So let's say, for example, we have a salt formed by the neutralization reaction between a weak acid and a weak base, like hydrofluoric acid and ammonia. This forms ammonium fluoride. What we need to do here is compare the Ka value of the conjugate acid, NH4+, with the Kb value of the conjugate base, F-, and we need to see which one is stronger. If the Ka is bigger, we've got the stronger acid. We can expect the solution is acidic. If the Kb is bigger, we've got a strong base. We can expect we have a weakly basic salt solution. So again, to summarize, if the Ka of the weak acid is greater than the Kb of the weak base, the salt is acidic. If the Kb of the weak base is greater than the Ka of the weak acid, the salt is basic. If they happen to be equal to one another, then the salt is neutral. All right, a couple questions for you to try. First, will a solution of NaCN be acidic, basic, or neutral? Second, will a solution of RbNO3 have a pH greater than, less than, or equal to NH7? And finally, will a solution of NH4F be acidic, basic, or neutral? Please pause the video and try these 3 problems. Okay, the answers here. For number 1, your cation is Na+. This is a group 1 metal cation, so that's a neutral cation, but Cn- is the conjugate base of a weak acid, and therefore it is a weak base, and we would expect this solution to be basic. Number 2, Rb, rubidium, Rb+. This is again a group 1 metal cation, which is neutral. And NO3-, this is the conjugate base of a strong acid. It is also neutral, meaning this solution is neutral and would have a pH equal to 7. And finally, number 3, we should note here that the Ka value of ammonium, NH4+, is slightly bigger than the Kb value of fluoride, the F-, and so we would expect this solution to be slightly acidic. All right, and we're going to end today by looking at calculating the pH of salt solutions. So what is the pH of a 0.15 molar solution of NH4Cl? Given that the Ka of NH4+ is 5.56 times 10 to the negative 10th. Oh, sorry, that shouldn't be here yet, but it'll become relevant in a moment. Okay, so let's start by writing out, sorry, my animations got slightly out of order there, but I will highlight the key information. We've got the concentration, we've got the salt we're dealing with, and we've got the given Ka value. Start by writing out the dissociation of that salt. Assume that it's going to be soluble unless told otherwise. So NH4Cl is going to dissociate into NH4+ and Cl-. Ionic compounds dissociate completely. So if you have a 0.15 molar concentration of NH4Cl, it is safe to assume you have 0.15 molar concentrations of both of these ions. Note here that Cl- is the conjugate base of a strong acid. It's the conjugate base of HCl, hydrochloric acid, so it will not react with water. but NH4 plus is the conjugate acid of a weak base. It's the conjugate acid of ammonia, NH3. So now we need to write out the dissociation reaction of NH4 plus. You can choose to include water, or you don't have to here. Typically I do, but to save myself some space, I chose not to here. So you could easily write NH4 plus H2O forms H3O plus and NH3, but this still gets the point across. The point here is that NH4 plus, since that is a weak acid, it partially dissociates. So it's a different symbol here, but this is still meant to represent that double or reversible arrow because the reaction can go in both directions. This forms H plus and NH3. We can set up our ice table. We've got an initial concentration of 0.15 molar for NH4 plus. We can assume that the H plus and NH3 are both 0. Everyone's coefficient is 1, so we're moving in the forward direction with a change of minus x for NH4 plus and plus x for both our products, giving equilibrium concentrations of 0.15 minus x for NH4 plus and just x for both the products. Now we can set up our Ka expression. Ka equals the concentration of H plus times the concentration of NH3 divided by the concentration of NH4 plus. You can plug these values into that expression and set it equal to the Ka value you were given. So x times x over 0.15 minus x is equal to 5.56 times 10 to the negative 10th. Note that this K value is very small, so we can use the small x approximation and cross off the minus x, which means, therefore, that x is equal to the square root of 5.56 times 10 to the negative 10th multiplied by 0.15. All I did here, I skipped an algebra step, but I multiplied the 0.15 from the left to the right, and then I square rooted both sides since I would have an x squared on top. You should find that x equals around 9.1324 times 10 to the negative 6th. This gives us the H plus concentration, and then recalling that pH is equal to the negative log of H plus, so pH equals the negative log of that x value, and finally we get the answer pH equals 5.04. Okay, a little more calculating the pH of salt solutions. So I'm going to show the work on this one as well. Calculate the pH of 0.15 molar NaCN given the Ka of HCN is 4.9 times 10 to the negative 10th. So we've got the salt NaCN, which dissociates to form Na plus and Cn minus. Again, you can assume it fully dissociates. Notice here on this problem we have a weak base instead. Na plus, a group 1 metal cation, is neutral, but Cn minus is a weak base. It's the conjugate base of the weak acid HCN. So then Cn minus will react with water to form HCN plus OH minus. So we write out our dissociation reaction. Then we set up the ice table. Concentration of Cn minus is 0.15 molar. H2O you can ignore because it's a liquid. The HCN and the OH minus are both going to start at 0. Everyone's coefficient is 1, so our changes are minus x, and plus x, giving equilibrium concentrations of 0.15 minus x and x for both products. Set up your Kb expression. Note that this should be a Kb expression because OH minus is one of the products, Cn minus is a weak base, OH minus is one of the products. So this is a Kb expression. Kb equals the concentration of OH minus times the concentration of HCN divided by the concentration of Cn minus. Plug your values in, x, and 0.15 minus x. Now before we can keep going here, note that you were given a Ka value, and one of the expressions we learned about earlier in this unit was that Kw equals Ka times Kb. So we can solve for Kb. Kb is equal to Kw divided by Ka, which would be 1 times 10 to the negative 14th, divided by 4.9 times 10 to the negative 10th. This gives a Kb value of 2.01 times 10 to the negative 5th. This is still a pretty small k value, so we can use the small x approximation here. So we can say that x squared over 0.15 is equal to that kb value we solved for here. And finally, x is equal to the square root of 2.041 times 10 to the negative fifth multiplied by 0.15. And to finish this problem off, you should find that x is equal to 0.00175, which gives us the OH minus concentration. We can use that to find the POH. POH is equal to the negative log of OH minus. Plug that value in. You get a POH of 2.757. And finally, the last step. These problems can be a little long. Use that equation we established earlier, pH plus POH equals 14, which means the pH equals 14 minus 2.757. Final answer, the pH is equal to 11.24. So these problems where you're asked to calculate the pH of the salt solutions can be long. To summarize the steps you want to follow, start by writing the dissociation of that ionic compound, then analyze the two ions, decide if either one of them are acidic or basic. Typically on these problems, only one of them will be acidic or basic. So on the first one we looked at, we had an acidic cation. On this one, we had a basic anion. Once you determine whether or not you have an acidic cation or a basic anion, write out your acid or base reaction, set up an ice table, solve for x, and then from there you can find the pH of the solution. All right, and that finally concludes lecture number 15, a bit of a long lecture, but a lot to cover here. I've got 4 additional practice problems that I would recommend that you try. So go ahead and pause the video, and then I'm going to show the answers on the next slide in just a moment. Here are the answers. That concludes lecture number 15. I hope you found this useful, and I hope you found all the explanations clear. I apologize if I stumbled at all, especially in part 1, or if I went a little too quickly. Please feel free to reach out to me either via email, or you can ask a question down in the comments below, and I will get back to you and help as best as I can. That's all for today. I'll see you in the next one. I hope you have a great day.